This is Saturn V, the rocket that took us to the moon. One of the biggest, most powerful precision machines ever conceived and built. But Saturn V was an expendable launch vehicle. Each could be used only once. With our nation and the free world increasingly reliant on space technology, the need to reduce costs, increase productivity, and expand our capabilities in space has become a major challenge. Recognizing the growing role space is playing in business, science, and defense, there is increasing international competition for the space dollar. In Japan and other foreign countries, launching systems are under development. The Ariane expendable launch vehicle, developed by the European Space Agency, is booking payloads. And these systems all feature an expensive throwaway launch vehicle. But continued use of expendable launch vehicles is a luxury we can no longer afford. The United States has achieved and maintained the leadership in space. Our continuing presence in space is essential to our economy, to science, and to our national security. America's reusable space shuttle offers the most cost-competitive and versatile transportation system for the routine access to and the exploitation of space. Opening the space environment to many new users, it is a vital factor in maintaining our technological superiority in this competitive world. To compare costs in today's dollars, it takes an average of $22 million to put a satellite into orbit with a Delta expendable launch vehicle. The cost of orbiting that same satellite in the space shuttle will be around $10 million in a shared flight. This is a major step in reducing the cost per payload of spaceflight. The space shuttle is the keystone of the United States space transportation system. A fleet of 4 shuttles is planned, each designed to fly at least 100 Earth orbital missions. The shuttle consists of 3 major components. First, the orbiter, most simply described as a space-going cargo vehicle, at home in the vacuum of space or in the atmosphere of Earth. It will carry a flight crew of from 2 to 7 men and women. In its 60-foot long, 15-foot diameter payload bay, it will eventually carry cargo weighing up to 65,000 pounds. Second, the external tank, holding over 1.5 million pounds of liquid propellant to supply the orbiter's main engines. The third major component, twin solid rocket boosters, which produce a combined thrust of over 5 million pounds for liftoff. In a typical shuttle mission, the 3 liquid-fueled main engines and the 2 solid rocket boosters will ignite, providing a combined thrust of 7 million pounds to lift the shuttle toward orbit. Two minutes later, the solid boosters will burn out, separate from the external tank, then parachute to a water landing and recovery in the Atlantic Ocean. The boosters will be refurbished and returned to service on a continuing basis. The orbiter's main engines, fed by the external tank, will burn for approximately 6 more minutes. Shortly before achieving orbit, the main engines will shut down and the external tank will be jettisoned. This empty metal shell will not be recovered, but will fall harmlessly into a remote ocean area. The orbiter will continue into orbit, powered by the engines of its orbital maneuvering system, which are fed with liquid propellant from onboard tanks. The orbit can be varied from 115 to 350 miles in altitude, depending on individual mission requirements. In orbit, many types of missions can be performed. Up to 4 satellites can be deployed on a single flight. Satellites can be repaired in orbit, refurbished or retrieved, and returned to Earth. Satellites are now observing the Earth, providing valuable information for the utilization of the resources of our planet. Space probes can be placed in Earth orbit, then launched on deep space and interplanetary missions. Already we have sent unmanned spacecraft to and beyond the planets. We have seen the swirling atmosphere of Jupiter and discovered another of its moons. We have plunged through the rings of Saturn, and we have seen volcanoes erupt on the alien moon called Io. The Space Shuttle will expand the effectiveness of these programs while reducing costs. In its payload bay, the orbiter can carry Space Lab, a modular manned scientific laboratory designed and built by the European Space Agency for use by the international scientific and industrial communities. Ready access to the zero gravity and vacuum of space will open this environment to industry, to investigate the production of new materials, highly pure chemicals, new crystal growth methods for electronics, new metal alloys, new and lower-cost pharmaceuticals. To stimulate the commercialization of space, NASA and McDonnell Douglas Astronautics Company are engaged in a joint venture to develop a new technique in pharmaceutical processing in space, to produce substances we cannot create in sufficient quantity or purity in ground-based facilities. With completion of the mission, the orbiter's payload bay doors will be closed and latched for re-entry. The crew will fire the engines of the orbital maneuvering system to leave orbit and re-enter the Earth's atmosphere. During atmospheric entry, surface temperatures on portions of the orbiter will reach up to 2,800 degrees Fahrenheit. Once through the heat of entry, the orbiter will fly like an airplane, an unpowered, high-speed glider. This is a flight of the test vehicle, the Enterprise, the pathfinder for orbiters to come. These approach and landing tests were successfully conducted in 1977 at NASA's Dryden Flight Research Center in California. After the returning orbiter lands, it will be readied for its next flight. The era of the Space Shuttle is about to dawn, but it didn't come about without great effort. In 1971, the need for lower-cost transportation into space on a routine basis was recognized. NASA was given the charter by the President and by Congress to design and build a reusable space shuttle. It meant establishing a team of government and private industry, a national network of contractors. To design and build the orbiter, a prime contract was awarded to Rockwell International. In turn, over 300 subcontractors produced many of the sections and systems that comprise this complex vehicle. Final assembly of the orbiters is completed at Rockwell plants in Southern California. In New Orleans, Martin Marietta builds the external tank. This 154-foot-long structure, with a diameter of just over 28.5 feet, contains over 1.5 million pounds of liquid hydrogen and liquid oxygen propellant at liftoff. Constructed of aluminum, its outer surface is coated with both spray-on and ablative insulation to help maintain the propellant at the proper temperature, minus 320 degrees, to help prevent ice from forming on the cold outer skin before ignition, and to protect the tank from atmospheric heating during ascent. The external tank for the first shuttle orbital flight test was delivered to the Kennedy Space Center in Florida on July 6, 1979. Thiokol Corporation in Utah is responsible for development of the solid rocket boosters, the largest solid propellant rockets ever built. Each is just under 150 feet long and over 12 feet in diameter. Constructed of weld-free, high-strength steel. Each rocket motor generates 2,650,000 pounds of thrust at sea level. Although this will be the first application of a solid propellant rocket as a primary launch vehicle for United States manned spaceflight, the technology is well developed and understood. The boosters for the first flight test have been delivered. They were received at the Kennedy Space Center in September 1979. To build the solid rocket boosters alone, contracts were let to 64 companies in 20 states, and this is just one of the 3 major shuttle components. In all, building the shuttle requires 50,000 people working for hundreds of contractors in 47 states. The space shuttle is a major development in high technology. 2 specific areas have produced the greatest challenge, pushing ahead the state of the art. 2 areas that have proved to be the pacing items for the first orbital flight test of the shuttle. Because of significant problems in these areas, major delays have occurred in the shuttle program. First is the development of the orbiter's main rocket engines. For their size, these liquid propellant engines are the most powerful ever built, producing 375,000 pounds of thrust at liftoff. This much thrust is generated by achieving an extremely high chamber pressure, 3,000 pounds per square inch, a major step forward in rocket technology. Besides containing such high pressures, the engines are lightweight and capable of being throttled down to 65% of thrust to control G-loadings on the shuttle during ascent. And they have been designed to perform at least 55 flights with minimum maintenance, another goal never before achieved in rocket engine design. Development of these new engines is the responsibility of the Marshall Space Flight Center in Alabama. To date, well over 500 tests have been run. While problems encountered were not totally unexpected in such a complex high-technology project, some did lead to program delays. When the flight configuration of 3 engines was run, some failures occurred which resulted in major slips in the schedule. One by one, the problems have been isolated and eliminated. Most were associated with the tremendous pressures and vibration levels which are developed. One significant contributor to these program delays was the inadvertent use of the wrong grade of welding wire in construction of the engines. This caused weaknesses in the welded areas, leading to failure under high-stress conditions. With the detection and correction of these problems, and with continual upgrading of the main engines, the 3 engine clusters have now begun to perform as planned. 4 successful firings, simulating the length and conditions of launch, at 100% of their rated thrust, have been conducted without incident. More than 70,000 seconds of the 80,000 seconds required firing times for flight readiness have been accomplished. The main engines for the first orbital flight test have been upgraded on a continuing basis. Previously stored at the Kennedy Space Center, they have been returned to the test stands in Mississippi for requalification prior to the flight. Another critical area of development which has contributed to program delays is the shuttle's unique thermal protection system. This is presently the pacing item in preparing for the first orbital flight. The thermal protection system is planned to be reusable over 100 flights with minimum maintenance. During re-entry, temperatures on the orbiter's surface will range from 400 to 2,800 degrees Fahrenheit. The temperature of the orbiter's aluminum skin must be kept below 350 degrees. Where surface temperatures will range from 2,300 to 2,800 degrees, reinforced carbon-carbon is used. However, this material is heavy and its use must be limited. Where temperatures will not exceed 750 degrees, coated Nomex fabric covers the aluminum. The major problem has been in providing thermal protection in the mid-range, from 750 to 2,300 degrees. A silica fiber material was developed for this purpose. It is a cast material containing about 93% void. It weighs only 9 pounds per cubic foot, about the density of balsa wood. Bonding of the tile to the orbiter has presented a major problem and program delay. It was determined that for attachment to the orbiter, the optimum size of the tiles is about 6 by 6 inches. 30,922 individual tiles are shaped to fit the contours of the orbiter. To alleviate stresses between the tiles and the aluminum skin, a flexible Nomex pad is mounted between the skin and the tiles. Where a stiff area of pad is joined to a lower strength area of tile, the tile tends to crack and loosen when stress is applied. Under tests, some failures have occurred at 50% of the tile's rated strength. To correct this, the bonding surfaces of the new tiles are strengthened with a substance that penetrates the tile about 1/10 of an inch and provides a thin layer of high strength for bonding to the Nomex felt pad, thus eliminating the problem. Tiles on the orbiter Columbia are being tested to assure the quality of the bond between the tile and the spacecraft. Tiles failing these tests, or that are in any way deemed questionable, are removed and replaced with strengthened tiles. During testing through the first quarter of 1980, over 15,000 tiles were tested and over 3,000 removed and replaced. Testing and bonding are proceeding at a rate which should allow completion by the end of summer 1980. The thermal protection system is showing good progress. The Columbia is being readied in the orbiter processing facility for an early fall rollout. The solid rocket boosters and external tank are in the vehicle assembly building at the Kennedy Space Center, awaiting the Columbia. The orbiter main rocket engines are performing to specifications and are no longer a pacing item. Launch Complex 39 has been modified for shuttle use and is ready. The Launch Control Center has been adapted for the shuttle. Staffing for an Apollo launch required 465 people. Only 100 are required for shuttle launches. The 15,000-foot-long landing strip at KSC will be the primary landing site for operational flights. The first orbital flight tests will land on the 11-mile-long lake bed at Edwards Air Force Base in California. And the orbiter processing facility is in full operation. The second orbiter in the shuttle fleet has already served as a structural test article and is now being reconfigured for flight. The airframe and aft fuselage are undergoing the necessary modifications. One half of the crew module component has been completed. Delivery date for the completed orbiter is the summer of 1982. Detailed component fabrication for the aft fuselage and crew module of the third orbiter has been underway for about a year. Soon, work will begin on the lower forward fuselage. Delivery is set for the fall of 1983. At the Johnson Space Center near Houston, 26 veteran astronauts and 35 new astronauts are being trained as pilots and mission specialists for the coming shuttle flights. Crews for the orbital flight tests are undergoing specific mission training. The crew of the first flight is astronaut John Young, commander, and veteran of 2 Gemini and 2 Apollo missions, and Robert Crippen, pilot. Included in this training are mission simulations in the shuttle simulators, which are linked to the Mission Operations Control Room, from which flights will be controlled. A second control room is being prepared for the exclusive use of the Air Force for control of Department of Defense flights from the Kennedy Space Center in Florida, and later from Vandenberg Air Force Base in California. Construction at Vandenberg began in 1978, with excavation completed in late 1979. Site preparation and construction are expected to begin in mid-1980. This phased-by-year military construction program is aimed at an initial shuttle launch from Vandenberg by mid-1984. As the shuttle nears its first flight test, members of the industrial, scientific, and defense communities are standing by. Of the 39 flights scheduled in the first 3 years, 35 are presently reserved for NASA, the Department of Defense, commercial, foreign, and military payloads. 152 separate payloads, which include 76 small, self-contained payloads, are already booked. to take advantage of this economical and versatile means of space transportation. The Department of Defense has urgent requirements for the shuttle. Should the shuttle not be available, the redesign of payloads meant for the 60 by 15-foot payload bay to the lesser capabilities of expendable launch vehicles would be a formidable and expensive task. The shuttle is nearly ready for its first orbital flight test, scheduled between November 1980 and March 1981. In the 1980s, we will expand the utilization of space, and space flight itself will be quite different from our previous era of space exploration in the 1960s and 70s. We stand at the beginning of a new and practical era in space technology. Spaceflight has become a necessity of modern civilization, essential to our economy, to scientific achievement, and to our national security. The space shuttle is the means by which we will maintain the leadership in space that we have achieved over the last 2 decades.